Hello. Today I want to talk about near-optimal linear algebra in the online and sliding window models. This is joint work by Vladimir Braverman, Petros Drineas, Karen Musco, Chris Musco, Jalaj Upadhyay, David Woodruff, and Samson Zhou. Let's start by breaking down some of the terms in the title. To understand the sliding window model, we first need to understand the streaming model of computation. Here, elements of some underlying dataset S arrive sequentially, and the goal is to evaluate or approximate some predetermined given function, using space, sublinear, and the size of the input. In the sliding window model, only the n most recent updates form the underlying dataset. So if we have a sequence of bits, and the window size is 8, then until we see 8 bits, everything we see will be in the underlying data set. But once we see the 9th bit, then the first bit will implicitly expire, and the underlying data set would be the 8 most recent bits. And this trend continues when we see the 10th bit, the 11th bit, and so on. The sliding window model emphasizes recent updates, and thus it's a bit more appropriate for time-sensitive applications in the unbounded streaming model. Now, there are different ways to describe updates in the streaming model, but in this talk, we'll focus on the row arrival model, where we have a matrix of dimension n by d, and we get rows of this matrix one at a time. These rows have dimension d, and until we see n rows, everything will be in the underlying matrix. But once we see more than n rows, then the previous rows implicitly expire, so that our underlying data set is just the n most recent rows. As I mentioned, the sliding window model is a good model for time-sensitive information. We already use tools from linear algebra in applications that are based on optimizing strategies and predicting future patterns based on past data. But we also don't want to use information that is outdated for these applications. So it seems like a natural idea to study numerical linear algebra in the sliding window model. In this talk, I'll first mention some results that we have for the sliding window model. I'll mention the algorithm, the analysis, and the intuition for these results. And at the end of the talk, I'll also mention some connections to the online model and how algorithms for one model may translate to algorithms in the other model. So first, I'll start with spectral sparsification. In this problem, we're given an accuracy parameter epsilon and a matrix of dimension n by d. And the goal is to find some other matrix M with dimensions m by d where little m is much less than n. And M needs to satisfy the property that for every x of dimension d, the 2 norm of mx is roughly the 2 norm of ax. It can be shown that such a matrix M will be able to approximate all cuts of a graph when A transpose A is a graph Laplacian. Moreover, by tweaking the input matrix A a bit, it can also be shown that this approach can approximately find the vector x that minimizes the 2 norm of ax minus b. And this is the form of least squares regression. So there are a couple of challenges to looking at this problem in the sliding window model. The natural approach would be to use the smooth histogram framework for sliding window algorithms. But the problem is that this framework is designed for functions that are smooth, which means they're well behaved. Moreover, these functions are scalar functions, whereas our scenario needs to deal with matrix functions. So it's not clear how to adapt the smooth histogram approach to our purposes. Another challenge is that a lot of these problems in the streaming model or the offline model use sketching techniques. But this is an approach that is challenging for the sliding window model because we cannot undo explorations that are implicit. For example, let's suppose that I have this matrix A and a sketching matrix P so that I always maintain the matrix P times A. Now the challenge is that when we get a new row to A, we'll see a row expire implicitly, so that we know the time of this row, but we don't know the row explicitly, and thus we cannot undo the effects of P times this expired row in the sketch that we maintain. And this is a general challenge for any sketching-based technique for the sliding window model. A third challenge is that other algorithms for these problems in the offline or streaming model use sampling techniques that are based on some measure of how important or unique each row is. And as the stream continues, or as we see each of the rows, we sample each of these rows with probability proportional to this quantity that measures how important these rows are. However, in our case, we seem to value rows that are more recent in addition to rows that are unique. And let me give an example for this. So suppose we have a matrix that only has 3 rows so far. Then we see the first row and we sample the first row because we have to sample the first row unless there are no other rows. Now we see the second row, and the second row has a large magnitude, but also it points in a direction that is different than the first row. So it's very unique compared to the first row, and thus we should be sampling the second row. On the other hand, when the third row arrives, not only is the magnitude of the third row small, but it points in the same direction as the second row. So a lot of the information in the third row is already captured by the information in the second row. So it looks like we did not sample the third row. But now let's suppose that the stream proceeds, and all rows before the third row expire, and all the new rows are zeros. So at the end of the stream, the matrix A consists of the rows that are in this blue box here. But now we can't possibly get a good approximate of A unless we've stored the third row, because all the remaining rows are zeros. So this implies that we should always store the most recent row. Thus, it seems like a new sense of importance that accounts for both how unique a row is and how recent a row is. This brings us to the concept of leverage scores. In the offline model, the leverage score of a row of a matrix is a quantity that captures how unique a row is. So the leverage score is this maximum characterization in the second line, and each row has a different score. Now, if we take A to be the matrix 1, 0, 1, 1, then we can compute the leverage scores of each row in this matrix. So if we take X to be the vector 1, negative 1, then we see that the first row has leverage score 1. If we take X to be the vector 0, 1, then we see that the second row also has leverage score 1. So this indicates that each of the rows are maximally important. And this makes sense because each of the rows point in different directions. So to get a good sketch of A, it seems like we do need both of these rows. Now, one good thing about this leverage score is that the maximum characterization of this leverage score is equal to some other quantity that I have at the bottom of the screen. And using this other quantity, it can easily be shown that the sum of the leverage scores is equal to D. Okay, so now let's go from leverage scores to adapting this intuition for our algorithm. So the leverage score of a row is described with respect to the matrix that the row is in. In particular, the leverage score of AI is with respect to A. But for us, rows before AI shouldn't count towards the importance of how row I should be sampled, because these rows previous to AI might be deleted. So instead, if we take B to be the submatrix consisting of the rows after AI, so that B is the yellow submatrix in the bottom diagram, then we define the reverse on-line leverage score of row AI with respect to this matrix B. Now we have the following algorithmic template. Suppose that at some point we have a matrix A that consists of many rows inside the blue box. But instead of maintaining this matrix A, we have a sketch of A, which only consists of a number of sampled and rescaled rows. In this case, the rows that we've sampled will be the red rows. Now a new row arrives, and we know that we should always store the new row based on our previous example. So we're going to store this new row, which corresponds to a new red row because we store it. Because we see a new row, then a old row has possibly expired and A will be updated, the matrix A. Now for each row that we've sampled, we want to decide whether or not to keep it with some probability. And this probability will be proportional to the reverse on-line leverage score that we discussed previously. So in particular, we'll sample this row A sub I1 with respect to the yellow submatrix of rows that correspond to rows that appear after A sub I1. And suppose for our purposes that we've sampled A sub I1 this process. So we choose to keep AI1, and then we go forward from there. Now we look at A sub I2. We sample A sub I2 with probability proportional to how important it is with respect to the yellow matrix consisting of rows that appear after A sub I2. Now we don't actually have this matrix that's yellow. We have a sketch instead of the 3 green rows. So we use that as a proxy to determine what probability we should keep A sub I2. And suppose for our purposes, we choose not to keep A sub I2. Then we progress forward and we sample A sub I3 with probability proportional to the rows that appear after A sub I3. And we do this iteratively until we've sampled until we've chosen to keep or discard all the rows that we've sampled so far. Finally, we should delete any expired rows because we have the timestamps explicitly for each of these expired rows. Note that this is in contrast to the sketching methods we described earlier, because there we do not have the rows explicitly, so we cannot undo effects of the sketch. Anyway, this describes the process for when a single row arrives. But now we see a new row, and we just repeat this procedure over and over again. So each time we'll look at the rows that we've already sampled, and we'll choose to keep them with some probability proportional to the importance of that row with respect to the rows that have appeared afterwards. To justify correctness of this algorithm, we show an invariant that proves that each sampled matrix gives a good proxy to how important a row is with respect to the rows that actually appear afterwards. This is done by a martingale argument in a monotonicity property of the online leverage scores. Thus, at the end of the algorithm, we output a matrix M such that the 2 norm of Mx is roughly equal to the 2 norm of Ax for all input vectors x. So this analyzes the correctness of the algorithm, but we still need to justify the space of the algorithm. Now recall that we sample each row with probability proportional to the reverse online leverage score. So it suffices to bound the sum of the reverse online leverage scores. It turns out that there's previous work that shows that this bound is at most roughly 1 over epsilon squared times d times some lower order terms. So we want to use this template to look at other problems. And the first problem we'll consider is low rank approximation. In this problem, we're given another accuracy parameter epsilon, and the goal is to find a matrix M with many fewer rows compared to A, such that the best rank K approximation to M is roughly the best rank K approximation to A. Whereas previously we used the leverage score to measure how important a row is, in offline approaches, the ridge leverage scores have been used to quantify how important a row is for a low-rank approximation. And this is just the leverage score along with some regularization parameter. So we use the same algorithmic template. And let's first suppose that we know lambda. This is an assumption that will waive in the future. So as before, we've kept a number of rows so far. And at each time, we sample each row that we've kept so far with probability proportional to the reverse online ridge leverage score. Again, we have a monotonicity property of the ridge leverage scores, along with a martingale argument to show correctness of this approach. But what I've swept under the rug is, again, how much space we maintain. And this is another issue that we'll need to resolve. So the two assumptions I haven't discussed is how to compute the regularization parameter lambda, and also how to analyze the number of rows that we've sampled. To handle the first issue, we first observe that it suffices to have a constant factor approximation to this regularization parameter lambda. And then we use known projection cost-preserving techniques to approximate this lambda. For the second approach, we need to bound the sum of the reverse online ridge leverage scores. To do this, we note that the reverse online ridge leverage scores, their sum is equal to the online ridge leverage scores of the matrix whose rows appear in the inverse order. So if AI is the matrix that consists of the first I rows of A, then it suffices just to bound the online ridge leverage scores of A. This can be done using a determinant process that compares the determinant of A transpose A plus a regularization term and relating this determinant to the sum of the ridge leverage scores. This can be done by separating the spectrum into small singular values and large singular values. And this is an approach that shows that the sum of the reverse online ridge leverage scores is approximately k log d. Because we bound the sum of the online ridge leverage scores, this actually also gives a space-efficient online algorithm for low-rank approximation, which I'll mention at the end of the talk. Okay, so we've completed our template. We've approximately computed lambda, and we've bounded the sum of the reverse online ridge leverage scores. Finally, we want to apply this template to the L1 subspace embedding problem. In this problem, we're again given an accuracy parameter epsilon and a matrix A with dimensions n by d. And now we want to output a matrix M such that the one norm of mx is roughly the one norm of ax for any input vector x. Now recall that the leverage score can be characterized by a maximization ratio. We similarly define the L1 sensitivity to be the corresponding maximization ratio with respect to an L1 norm instead of an L2 norm. Now we use the template that we described before, where we sample each row with probability proportional to the L1 sensitivity. We show that the L1 sensitivities obey another monotonicity property, and we use a martingale and a net argument to show correctness of this algorithm. So in other words, we showed that our matrix M that we output does satisfy the property that the 1 over mx is approximately the 1 over ax for any input vector x. Again, we still have an issue that we haven't actually bounded the sum of the online sensitivities, and this will key us in on the number of rows we sampled because we sample each row with probability proportional to its online sensitivity. To bound the sum of the reverse online L1 sensitivities, we first show a structural theorem that says that for any input matrix A and a regularization matrix B, there exists a scaling W of at most half of the rows of A, so that the online leverage scores of WA with respect to B concatenated with WA are at most 2D over N. Note that this is the online leverage scores and not the online L1 sensitivities. Then we give another theorem that says that if the leverage scores of a matrix A are uniformly bounded, then so are the L1 sensitivities. Thus, this gives us some way to uniformly bound the online L1 sensitivities. Then we can show that the sum of the online sensitivities is roughly d log n, where I'm omitting some condition number terms. We actually show a similar theorem for online Lewis weights, which is a generalization of Lewis weights, which is another way to get L1 subspace embeddings. This is an approach that was previously considered by Cohen and Peng. In summary, this template allows us to get algorithms for spectral sparsification, low-rank approximation, and L1 subspace embeddings in the sliding window model. This approach also gives us many key results and properties in the online model. In the online model, we again have an underlying dataset S that arrives sequentially, and the goal is again to evaluate or approximate some predetermined given function. Now, it's not always a constraint to use space sublinear in the size of the input in the online model, but for our purposes, we will restrict our algorithms to have space that is sublinear in the size of the input. But the crucial part of the online model is that each time when we get some update to S, we have to make an irrevocable decision to the output. For example, if we're sampling rows of S, at each time when we see a row, we have to either keep it or discard it forever. Our results are that we obtain online algorithms for low-rank approximation, row subset selection, PCA, and L1 subspace embedding. The key property for all of our algorithms is that we are able to get a handle on the sum of the online ridge leverage scores, or the online L1 sensitivities. Moreover, we display a connection between online algorithms and sliding window algorithms in the other direction by showing that if we have an online algorithm, these often yield what we call an online core set, which is an algorithm whose output can be used to approximate all prefixes of a stream. We show that online core sets give deterministic sliding window algorithms, and thus we get deterministic sliding window algorithms for spectral sparsification, low-rank approximation, and L1 subspace embeddings. For more information on our results, please see our paper, and thank you for listening to our talk.